Yeah, so welcome for me to this CASA distinguished lecture. And I'm super happy and have a great pleasure to introduce Lorenzo Cavallaro. Um, and first of all, let's say a little bit about where he's coming from. So he's currently a full professor at King's College London. And before that, he visited a lot of interesting security places, including our friends in Santa Barbara, including Stony Brooks, including Free University of Amsterdam with Herbert Voss. And also he had a stay at Royal Holloway for, I think, a couple of years, if I recall this correctly. And what makes this talk interesting to you? So if I look at the background of Lorenzo, I would say it's a system security background. So he has been working on taint analysis, malware analysis, program analysis things. So he's not a machine learning person from the start, but he now looks a lot into machine learning and adversarial machine learning. And I think this is always interesting if people somehow bridge backgrounds or if they bridge disciplines. And I like about Lorenzo's work that he tries to keep on the systems classes when looking at the machine learning problems. And this is also the case in this talk here, because we are looking now at the problem space. And this is where we as security people work in, and not some fantasy space where sometimes the machine learning people are working in. And I'm super happy and looking forward to this talk to learn about problem space attacks. Lorenzo, please.
Thank you, Corin. I mean, this is a great introduction. Probably the best introduction I've ever had. I couldn't ask for more, but now that I know that you give such a great introduction, I'm going to ask you all the time to introduce me, of course, Okay. Thank you very much. You've been way too kind. I mean, Conrad and I know each other. So of course, Conrad is too biased and it's too kind. He's a too kind person. So don't trust everything that he says, of course, when it comes about me. About other things, machine learning specifically, trust him, of course, machine learning and security. So, okay, so the introduction, I guess Conrad really touched on already the most interesting point. And the way that I wanted to start it is to say, as if 2020 was not grim enough, and let's hope that 2021 was a lot better, we can, of course, mouse is here, we can imagine even something worse, a dystopian future where pandas are just forbidden. So the only reason is that they are too cute. I mean, I know that we all love pandas. We just picture panda chewing up on a bamboo stick. And they're really cute, they're cute panda bears, but they're just been forbidden in the community because they are too cute. And you can see the community relies on computer vision systems and machine learning systems to actually deep learning systems, of course, to check whether there are pandas around. And if this is true, then pandas are just jailed and forbidden. They're banned from the city. Very grim future. But however, even though you might think that panda just chew on bamboo, and it takes a lot of bamboo to actually get enough energy, so the panda are actually fluent in math. So they do remember that there is so they actually look at one of the seminar paper in deep learning security, where brings to light the interesting intricacies of deep learning when considered in security context, and they come up with a plan. So in this paper, they remember that it is possible actually to fool such deep learning systems, so machine learning systems. In what way? So they remember that they can add a perturbation, some adversarial noise to an image to actually make the classifier perform a wrong prediction. So in the paper, they remember that there is their own pictures of a panda that a classifier classifies with a certain confidence. And then you can add a specifically crafted, optimized adversarial perturbation that we can imagine just as white noise, well, not white noise, but you can imagine as sort of a noise that added on top of the original image misclassifies the image as a gibbon, for instance, with its own confidence. So the panda says, this is really interesting. And I'm going to rely on this knowledge to actually do the same, but I have to do it in the physical world. So I'm not dealing with pictures here, but I have to do it in the physical world. That's not a problem, okay? And the tricky point here is that now the panda thinks, okay, what is the optimal perturbation that I can add to a mask that I'm going to wear to actually fool the systems like when I walk on the street? So the panda goes to the costume shop And so unfortunately, it already faces a first challenge. So the optimal perturbation is not available. It's not available not because it is sold out. It's not available because although the optimal perturbation exists in the feature space, it doesn't exist in the real world. For instance, you can imagine that there's no printer, there's no technology that they can print out that specific optimal noise so that you can misclassify an original image, okay? But that's all right. So there are other disguises that the panda can choose from that still serves the purpose. And for instance, in the costume shop, the panda finds out that there is a fox or a wolf mask. So the panda says, okay, I'm going to go with that. I just wear the mask and I can actually go around happily. But the problem is that the panda is fine here on its face, but there's still a lot of artifacts, a lot of features that give away in the real world that he is a panda. So panda bear, a little bit of a chubby belly, and the panda four, and the color of the panda four. So in this case, this is again, reject the panda, say, no, you are a panda. You try to disguise yourself as something else, but I caught you because in the problem space, that transformation is not enough to fool the system. So let's try to understand a little bit better what happened. So when we do when we reason about adversarial machine learning in the feature space, like think about this on image classification tasks, we start off with an image, like we mentioned earlier, like a panda image, to which correspond a feature vector X. Then we add a perturbation, which is this optimal noise, optimal adversarial noise that whenever it is added on top of the original image, creates this adversarial image that has a corresponding embedding X plus delta. Now, usually we find delta by solving an optimization problem that aims at minimizing, for instance, the sum of the pixels that you make the perturbation of, because you want the target image, so the perturbed image, the adversarial image, still to look like a panda to a human eye, for instance. And also we try to minimize the loss of the target class because you want to have the panda misclassified as the target class, a given, for instance, okay? So this is pretty much a typical pipeline of adversarial machine learning in the feature space, in image classification tasks, for instance. But let's see what happens in the problem space, okay? So when the panda, you remember, had to go to this costume shop and it doesn't find this optimal image because it cannot exist, it doesn't exist in the real world, so it's settled for something different. So let's try to follow this analogy and think about software, for instance. So something in the problem space, something that is a little bit disconnected from images, something that we can see. So think about an application. So we have an application to which it corresponds a feature space object X. We add again to this image a perturbation. For instance, by means of transformation, we can add APIs, we can add bytes to this original software, and we end up with an adversarial application, okay? So the reason is still the same. However, in this case, we may no longer be necessarily interested in minimizing the perturbation that we perform to create an adversarial object. Why? Because contrary to what we had earlier, there's no visual cue, there's no visual effect at the end. So we don't need to satisfy that constraint. So here, in a way, we have a little bit more freedom. We can add more bytes, we can add more APIs because there's no easy way for us to understand whether a software, a piece of software has been manipulated or not. However, there might be other constraints that we need to consider. For instance, does the transformation generate a realistic object? Can I run it? Does it crash? Does it preserve the semantics that the original piece of software wanted to achieve? And so forth and so on. So can we come up with some general constraints that actually are valid in this problem space? So the moment that we stop reasoning just about numbers in the feature space, and we start reasoning about the implication that we have in the real world, in software or in other domains that are representative of problem space objects. So, and here we have also another problem. So in the normal procedure, when you generate an adversarial object, we start off from an object X, we find out the perturbation, we see in a second how we find this perturbation, and we generate X plus delta. And from this X plus delta, we have created an adversarial image that also exists in the image space. But now here, once we have this adversarial object, how do we go back to the adversarial application? So it's a bit unclear how we can generate code, for instance, automatically from this adversarial perturbation that we have identified to go back to the original piece of code. And this is known as the inverse feature mapping problem, which is actually really our elephant in the room. So again, in a classical example of problem space adversarial machine learning on images, we have our image. We do have a function that maps this image to a feature space, to an embedding, and we perform the attack. We find this perturbation, the optimal perturbation, and the feature mapping fee is differentiable, so we can backpropagate this perturbation back to the input to generate the adversarial image. Now, in the problem space, this is no longer true because in general, the feature mapping fee is neither invertible nor differentiable. So we cannot really backpropagate anything to the input space. So how do we do this? So this is one of the challenges that we need to solve. And we need to understand what are the implications to reason about problem space at the same time. The point I'm trying to make is that we don't have to forget about feature space attacks. Absolutely not. They play a fundamental role even in this context. And we'll see in a second what is this role. But we need to understand that once you move into a problem space, there are other implications that you need to consider. So in the past, there have been several problem space attack papers on different application domains, Android malware, Windows malware, PDF malware, network traffic, and so forth and so on. And they've been really inspirational for us to start reasoning about this problem. However, it was a little bit tricky for us to understand what is the state of the art and whether there is a unified and principled way to reason about problem space adversarial attacks and how, therefore, we can advance the field in a more systematic way. So this actually led us to the work that I'm describing, which basically it has two main big contributions. So one is a little bit more theoretical, and the other one is a practical contribution. So the theoretical contributions that we try to reformulate adversarial machine learning in the context of problem space attacks. So we'll see what is the relationship between feature space attacks and problem space attacks. And also we try to provide in the form of theorems with proofs, some actionable points that we hope the community can actually leverage on when start reasoning about adversarial machine learning in the problem space, not necessarily on software, but on different domains, network traffic analysis, text domains, and so forth, and so on, for instance. The second contribution is that so this reformulation allows us to reason about adversarial machine learning in the problem space in a more principled perspective. And therefore, we're able to identify gaps of previous work and to instantiate an attack that is an end-to-end adversarial malware generation attack on Android systems at scale, where we do show that it's possible to evade also solutions that were specifically designed to protect against this problem in the feature space. And we'll see, what are the implications of this reasoning. Just for clarifying, because the problem is really broad and we haven't really thoroughly examined the full spectrum of adversarial machine learning, but we focus specifically on evasion attacks. And also our running example is code. So we reason about software and we reason about test evasion attacks. Okay, so we don't consider any poisoning attacks, for instance, or membership inference attacks, and so forth and so on. Okay, so let's have a look at the formalization. And let's start reasoning first at what are the problem space constraints that we believe we need to reason about when we start reasoning about adversarial machine learning attacks in the problem space. As mentioned earlier, we are no longer necessarily interested in keeping the perturbation to a minimum, so to minimize the perturbation. But there are other problem space constraints that we need to consider. The first one is, for instance, a set of available transformations. So we need to identify what are the set of available transformations that can help us to alter the problem space objects. For instance, we can add an API, and this transformation will induce a perturbation, of course, in the feature space. So for instance, we can, in the context of software, we can add API, we can add strings, we can add bytes. And or of course, we can also remove API, strings, and bytes. These are all available transformations that we may rely on. Of course, when we perform these actions, specifically removal, but also addition, depending on how you do the addition, we need to pay particular attention to not remove any specific behavior that we would like the original software to maintain. So in the context of adversarial machine learning attacks in the problem space that we are considering, our goal is to take a malware that is being classified as malicious, generate an adversarial malware, an object that is no longer classified as malicious, so it's misclassified as benign, but it still preserves its original malicious semantics, because otherwise, although you are able to bypass the classifier, then the attack is, there's no threat anymore, because the malware doesn't have its malicious behavior retained anymore. And of course, the combination of addition and removal, you can also build on that to modify specific actions in terms of features, API, strings, or byte, for instance. Okay, then the second constraint that we need to consider is a constraint that preserves the semantics that we're interested in, as mentioned earlier. For instance, if you look at this very artificial and simplified control flow graph, you can see that you can reach to the malicious node only by progressing through the blue nodes and the edges that are directly connect these nodes. So removing any of these edges will actually cripple the functionality of the malware. So that is a transformation that we could use, but it's a valid transformation, but it would violate the preservation of semantics. So although we cannot, in this specific example, remove any edges or nodes, we can absolutely add edges and spurious node. And if that addition would help us to then induce a perturbation in the feature space that makes our malware misclassified, then this is a great and successful problem space perturbation. However, the problem here is that how can we verify that we can preserve the semantic? From a theoretical perspective, this is undecidable. So we cannot have an algorithm that tells us whether this holds all the time. But however, we could perhaps design a test suite that exercise the adversarial object to make sure that the behavior that we would like to preserve is actually preserved. Or, as we'll see in our attack, we could actually do this by design, by construction. For instance, by adding no operation or making sure that the code that we're adding is never executed, but that is considered by the classifier whenever it analyzes the program in the feature extraction phase of the machine learning pipeline. Another interesting constraint that we believe we need to reason about is about plausibility. So we can add and remove, so we can identify a set of transformation to add and remove APIs, for instance. We can make sure also to preserve the semantics. But if you scrutinize the object, does it look legit? Does it look like a realistic piece of software, or it looks like, there's been some manipulation that actually gives away the fact that this is not a legitimate piece of software? For instance, we can add these APIs and making these APIs disconnected between each other. So if you look at the code, or if you analyze the code automatically, you see that these APIs are there, but they're never invoked, they're never collected, they're never connected to the normal execution flow of the program. So this is something important we need to consider. So plausibility. And finally, and also here, of course, like for the preservation of semantics, how can we guarantee plausibility is, again, by either defining test suite or by construction. So taking the normal precautions during mutation. So another constraint that we need to consider finally is something that usually or often is overlooked, and it's the robustness to pre-processing. So you can imagine that you can add valid transformation that preserve the semantics, but that can be easily removed by some analysis, some program analysis, without even entering the machine learning pipeline. For instance, if you add a spurious byte at the end of the program, if they are analyzed by the feature engineering, the feature extraction process, will be picked up and will influence the classifier. But you can absolutely design a program analysis phase before the object is analyzed by machine learning, the machine learning pipeline, that actually scrapes off all the bytes that are just appended at the end of the file, because these bytes will never be executed, will never be loaded, right? So in this case, your perturbation, so the transformations that induce a perturbation will actually be scraped off. So the malware doesn't even retain the adversarial component because it doesn't even reach the machine learning pipeline. So these all constraints, we should try to reason about these all constraints all together. And this is the animation, of course. And let's try to understand now what is the effect that these constraints induce in our reasoning. So here we have a simplified view of two features. So we have two feature x1, x2, and then we show the gradient, and the arrow identifies the direction of the gradient that goes from the red area on the right-hand side where malicious points are located towards the blue area where benign points are located. And in this area, for instance, we can already, and let's imagine that we want to create an adversarial example. So we can already start by saying that we are only concerned about creating an adversarial example by adding some features. Because again, if we remove features, there is a risk that we don't preserve the semantics. Okay, so let's just add these features. And in this whole region, we can identify already a sub-region that's called a feature space feasibility region, where all the points that we're interested in are contained in there. And within this region, we can also find or identify two sub-regions that we call the problem space feasibility region. So these are the points. So these regions contain the points that satisfy all the constraints that we just mentioned. Now, how do we create an adversarial object? Okay, we start off with an object X that belongs to in the red region, and it is in the problem space feasibility region because we start off with a real object, a real malware, a real program that is malicious. Then we perform our adversarial attack, and we then therefore backpropagate the gradient, the perturbation towards the blue part. And we identify, for instance, a point x plus delta star, where delta star is this optimal feature space perturbation that creates this adversarial object. But this adversarial object is in the feature space. So it's in our feature space feasibility region, which is fine, but it's in the feature space. So it's not in the problem space feasibility region of the benign points. So in a way, we need now from that point sort of project our adversarial object onto the problem space feasibility region of benign objects. And this projection adds something interesting that we usually don't have when reasoning about adversarial machine learning attacks at test time in the feature space. So it adds that eta term in the adversarial object. And that eta is what we call the side effect features. So these side effect features are not part of the attack. So the features that we consider, the perturbation we consider for the attack is this delta star. But because the point lies into a feature space feasibility region, not necessarily into a problem space feasibility region, we need to project this point onto this problem space feasibility region by satisfying the constraints that we just mentioned earlier. And this projection adds a bunch of other features that are a side effect of the fact that we want to move from the feature space feasibility region onto the problem space feasibility region. And we need to reason about the implications of having the side effect features. So a couple of actionable points before we move forward. First is that for how we frame the rest of the conversation, it is necessary first to find, or it's easier at least, to find a feature space attack. So if there is a necessary condition we have in the paper for problem space attacks, for the existence of problem space attacks. So a problem space attacks exist. So if we have if we have a feature space attack, then we can start reasoning about whether we have a problem space attack. In this context, if we cannot find a feature space attack, then we cannot generate a problem space attack. Now, if we do have a feature space attack and we can approximate the inverse, feature mapping function, then we can generate a problem space attack. So as you can see here, on the right-hand side, we have our reformulation of adversarial machine learning attacks in the problem space. So the reformulation is really is shaped from the original formulation of adversarial machine learning attacks in the feature space, but with the addition of all the constraints that we need to consider in the problem space, without necessarily being constrained by finding an optimal minimal perturbation, for the reason that we just mentioned. So this reformulation helped us actually to go back to prior work and actually to look not just at the software domain, but more broadly about work that explored adversarial machine learning in different application domains. And we were able to then identify, thanks to this principled reasoning, where the limitations or the part where we could improve our reasoning and understanding of adversarial machine learning attacks in the problem space. So in the paper, so we've published this work in Oakland 2020, and in the paper we have a fairly big table. It's not aesthetically pleasing. We spent some time really to try to make it more aesthetically pleasing. We failed at that. But in the table, we tried to capture really adversarial machine learning attacks in different problem space application domains, from the usual image and facial recognitions, and speech recognition, but also onto the others that I just mentioned: text classification, Windows malware, Android malware, JavaScript, malicious JavaScript, PDF, and so forth and so on. And we have a way to actually identify now and compare this work in the context of our reformulation of adversarial machine learning attacks in the problem space. This helped us actually now to move on to the attack that we designed for Android malware. So our goal here is to take Android malware that had classified as malicious and generate, so having an end-to-end system that generate adversarial Android malware that are misclassified as benign. So let's try to see the settings first. So prior work, of course, was fundamental and pivotal for us to really, really appreciate and understand the limitations of the reasoning that we believe the community had on understanding adversarial machine learning attack in this context. So we are part of the community. So we started doing this work because when we started, so actually a little bit of an anecdotal story here. So the work started just with the Android attack because we wanted to explore that. And as we were working on it, we started to understand that the problem was a little bit more complex than we had imagined. And by backtracking a little bit, we came out with this idea that we need probably a reformulation of adversarial machine learning in problem space context. And so we identified, therefore, the limitations of prior work. And then thanks to our reformulation, we were able to have a more principled reasoning about adversarial machine learning attack in the problem space, and specifically in this Android malware, adversarial malware. So let's have a look at how the attack works. So a very high level view of this. And by the way, all the animations here are the great work of Fergus, one of our PhD students in the group. Amazing animation. So let's say that you are a malware. So you are an Android malware. You go to the doctor, say, doctor, I need really to be misclassified as benign software. So the doctor say, no problem, I can help you. And the way that we work is just by leveraging on software transplantation. So the idea, and I'm fast forwarding a little bit, but the idea is to have a corpus of benign applications to which we harvest the gadget of interesting pieces of code that is realistic, and we transplant this gadget that correspond to a valuable transformation that we want to introduce in the malicious software. We transplant it into the malicious software so that this is something that is needed to fool the classifier. So the available transformations, we add code through automated software transplantation. We preserve the semantic of the malware because this code that we add, which is realistic, we just don't add a single API, but we add a slice that contains all the related information, and we'll see in a second what I mean by this, of the code. So this snippet of code, this gadget, what we call gadget, is never executed. So we wrapped basically this gadget around opaque predicate. So around something that is also hard to identify statically whether it's going to be executed or not. Because again, if statically you can identify that there is some bad code, then you can have a dead code elimination phase that actually scrape off the adversarial code transformation. But in our case, we wanted to have an opaque predicate so that we wanted to make it hard for an analyst to identify whether this is executed or not. But in reality, of course, the code that we introduce is never executed. We provide robustness to pre-processing because we introduce and plausibility at the same time, because as mentioned earlier, we don't introduce disconnected APIs or disconnected transformations. We transplant a realistic piece of code that comes from a corpus of benign software. Okay, so let's see how this works in a little bit more detail. So we identify, for instance, a feature that we want to transplant into the malware. And from that features, we then perform a backward slice so that we identify all the information that is needed to reach the creation of that specific feature. So in the Android terminology, think about the fact that we want to have an activity, we want to insert an activity, and therefore in the backward slice, we collect all the dependencies, all the intent, for instance, that are needed to create that activity. Then once we have this information, we perform a forward slice to actually gather all the activity definitions and recursively collect dependencies. So for instance, permissions that are used, complex object that are used as part of the code of this snippet code, we collect that object definition, because at the end of the day, we want to have a realistic piece of gadget, so piece of code that is transplanted into the software and it's compiled. Like, so the code, the final code is a realistic piece of code. We then save this gadget in what we called an icebox. So the analogy about software, organ transplantation, of course. It's a database of all the gadgets that would be useful for adversarial attacks. And then let's see how we pick these gadgets, okay? So let's start off by saying that we have a trained model. For the sake of simplicity, or not just simplicity, the whole attack is based on a linear classifier. So I'll provide you some details later on about exactly what we actually explore. But we start out with a linear classifier because it's a lot easier to reason about the whole concept. So, but let's assume that you have a classifier that is trained as you see in the slide. So we have the red gradients where we have malicious points. We have the green part where we have benign points. The histograms represent the features importance for malicious classes for the benign class, and then we have our decision boundary that divides these two classes. So we first pick the features with the greatest benign weight. Then we go and look into our database, into our icebox for the corresponding gadget, for the gadget whose code corresponds to this feature. So say that the feature corresponds to a specific activity, then we go into our database to identify what gadgets have that specific activity. Then we take that gadget we wrap it into an opaque predicate, and we transplant it into the malicious software. And so that it's never executed. Then we repeat this process over and over and over. And then you can imagine that the more we do this, we are basically taking benign features, the more you can see the point moving from the malicious point, moving from the malicious problem space feasibility region onto the problem space feasibility region of the benign point. Okay. Now, you remember that, however, it's not as simple as we have depicted. So this will work if actually the points will actually migrate between problem space feasibility regions seamlessly. But we have seen, remember that we had that image with the two features and the gradient, the direction of the gradient. We see that while starting with the problem space object, and you perform an attack in the feature space, therefore the object you obtain with the optimal perturbation leads you to a feasibility region, but you want to go to the problem space feasibility region of the benign points. So that requires you to reason about the side effect features. And in that case, we do have side effect features, of course, because the gadgets that we have does not just include that specific transformation, the activity, but it includes the slices, so the backward and forward slices. So those slices correspond to other transformations that correspond to other features. Therefore, what we do actually, we have several contributions in an individual gadget of benign and malicious features. Now, because we're reasoning about linear classifiers, it's a lot easier now to understand the contribution of that specific gadget to the final classification. So we can rank basically these gadgets according to the overall benign contribution, and then select the gadget that contributes the most in a greedy algorithm to the misclassification. And we progress until we are sure that the point it crosses the boundary. So in our experimental settings, we have a couple of experimental settings where we perform a low confidence and a high confidence attack, where we're just concerned about either having the point crossing the boundary or having the point being pushed a little bit further towards the first interquartile of the benign distribution. Okay, and this is just the way that it works. So let's recap a little, or let's explain a little bit the experimental settings now. We evaluated our approach on around 170,000 Android applications, of which 10% are malware. This dataset covers the period from January 2017 to December 2018, and is collected by Andrew Zhu. Then we split this data set for the training purposes into 66% training and 34% testing, random split, to sort of remove concept drift as a variable. So you just wanted to reason about adversarial machine learning, and we try to remove any experimental settings that might actually influence the result because of other variables that we couldn't control. Concept drift being one of them, for instance. If you're interested about concept drift or the effect of concept drift, I just link a couple of papers that we worked on in the past that explores classification with rejection, so transcend using X17, and the effect of concept drift in machine learning classifications for malware using X in SEC 2019. In terms of algorithms that we focused our evaluation, we focused on Drebin and SecSVM. So Drebin it's a very simple algorithm that relies on a linear SVM and on a binary feature space. It's simple, but it still provide pretty good detection results on a typical classification task of goodware and malware. And then we evaluated also how our attack or how our attack success rate would be hindered, if at all, by a hardened version of this linear SVM that basically clumped the weight of the classifier to force the attacker to make a much larger perturbation across different features. okay? So that the weights that are clamped and they are more evenly distributed across the features, instead of having in a linear SVM, in a normal linear SVM case where you have just fewer features that have very high weights, and then you have a long tail. And as mentioned earlier, as in terms of attack configuration, we have a low confidence attack and a high confidence attack, where basically low confidence attack, we just aim at bypassing, at crossing over the boundary decision. And with a high confidence, we aim at pushing the malicious adversarial point towards the first quartile of the benign distribution. So what is the impact on the feature space? And here, I guess, the main point that I wanted to show you is that if you look at the attack success rate, which is on the y-axis, and on the x-axis, we have the number of features we have to add, we'll see that even with a hardened classifier, we are able to achieve 100% attack success rate by adding just a handful of features. So you might say that 100, let's say 120 features will lead us to 100% attack success rate, even on the hardened classifier in a high confidence attack settings. Now you have to understand that, however, these 120 features are out of 10,000 features, out of a feature space that is that has more than 10,000 features. So we picked the top 10,000 because it is actually much larger. It's very sparse. So this is expected in a way, because again, here we're not really concerned about minimizing the perturbation. Here we're concerned about making sure that other constraints are satisfied. So it is clear that we can bypass hardened classifier. But what we wanted to understand is, can you give away the fact that an application is being manipulated and is adversarial? So to understand this, we tried to look at some statistics that perhaps normal applications have. And our hope is that, our hope with the attacker hat on, our hope is that the statistics of these malicious adversarial applications, they're still very much similar to normal applications, so that it's not easy to give away the fact that there's been an adversarially generated application. So in this case, for instance, we checked first the application size. So, okay, we have to add features. In particular, we have to add several gadgets that are just not made by one feature, but several features, and to which corresponds not just one line of code, an API invocation, but the whole slice, which can be fairly complex. And we wanted to understand, okay, this influenced surely the size of the application, but how does this compare to normal applications? And we can see that in general, the majority of the applications, they really fall within a typical statistics of applications. So they fall within the average plus or minus 3 times the standard deviation of the size of the whole application of benign software. So by looking at application size, you cannot really say that this is an adversarial example. And then we ask ourselves, okay, there are other statistics that we can actually compute to understand whether this is true in general or not. And in the paper, we report this result on size of the application, the average cyclomatic complexity, permissions, API calls, URLs, and so forth and so on. And for all of this, we basically have adversarial objects that fall within a typical distribution. So despite you can perform not just the minimal perturbation, but the perturbation that you need to break hardened classifiers to actually have adversarial objects misclassified as benign, we still don't give away any artifact that basically would let you understand that this is an adversarial generated object or not. And finally, you might just want to ask whether this is a time-consuming task. It is a fairly time-consuming task, and so the whole pipeline, in considering the program analysis bit about the gadget identification, the backward slicing, the forward slicing, training the model, and so forth and so on, and performing the feature space attack, and then reason about the side effect features. But in general, on average, we are able to generate objects in one object in less than 2 minutes. So we can actually, we argue that this is something that you can do at large scale. So this basically leads us to conclude my talk. And what we try to reason about is, so we found adversarial machine learning really fascinating from an intellectual perspective. We started to reason about adversarial machine learning on something that we were more familiar with, software. So as Conrad mentioned, comes from program analysis. And in this process, we realized that the typical formulation of adversarial machine learning attack in the feature space, what you have usually on paper on images or related application domains, we felt that didn't quite describe all the challenges or all the issues that you might find when reasoning about problem space. When reasoning about all the situations in which the feature space is neither invertible nor differentiable. The feature mapping is neither invertible nor differentiable. And this led us basically to start reasoning about a way that we could reformulate, hopefully, adversarial machine learning in the context of problem space, so that our hope is that now we have something that is a little bit more principled to help us reasoning about this problem and how we can perhaps come up with solutions that withstand this type of attacks. And of course, problem space attacks research is just the beginning, so we'll need a lot of help and more research into this fantastic and fascinating topic. Thank you, everyone, for tuning in, and I'll be taking questions very happily. Thanks.